Hello, everyone. Thank you for being here for the last presentation. I'm Simon. I've studied Faculty of Physics at the University of Bucharest. I finished my PhD earlier this year, and this is part of my thesis. The subject was fireball networks and photometry. So let's remind ourselves a bit what happens when an object enters the atmosphere. So we basically have radiation that we see, that we enjoy with optical cameras. Then we have plenty of other processes. This is fairly complex phenomenon. I'll not get into the details. What we're focusing on is acoustic waves that happens from the ablation cylindrical shock wave. But also a point source explosion can also cause an acoustic wave that travels into the atmosphere. And in the case of really large objects, luckily these are very rare. It will also cause surface impact and generate seismic waves. But again, the point source explosion can also generate the shock wave that couples with the ground and travels to the seismic station, and the ablation itself can couple with the ground at the seismic station location. And most of the time, the ground coupling of the explosion travels faster than the cylindrical shock wave, because this is a more dense medium. So one idea is to make the multi-sensor observation using the atmosphere as a detector. So that's what we did. We studied the FRIPON database. We tried to find such objects. This was part of a large collaboration. Francois was involved. That was also involved with the team at the Oldenburg University, team at Astronomical Institute of the Romanian Academy. So, by the way, this is the header of the database. This is an open access. You can access it just by clicking here. We found one very spectacular fireball across the Pyrenean mountain range. This happened between France and Spain over the Pyrenean mountains. This was detected on the Hendaye station. There was quite a cloudy sky in France at the time, kind of like the last couple of days here. And this was also observed from DAX, but this time from a more uniform cloud filter, and this helped with the trajectory estimation and the accuracy of the astrometry. But then again, this was observed from Montsec station in Spain. This was more than 250 kilometers away. This was observed over the layer of clouds, because over at Montsec it was a clear sky, and this helped with the photometry. And based on this three station, we can reconstruct the trajectory, and we have we know that the object entered the atmosphere at about 88 kilometers and lasted down to 26. And based on these measurements, we could compute the energy estimation based on the dynamics. But this was also detected by several cameras, several stations of the Spanish seismic network. And this helped to estimate, to have an acoustic estimate of the energy. The airwave traveled all the way to Tunisia at the CDBDO station, more than 1,300 kilometers away. So this resulted in an independent estimate of infrasound, and we also have the radiation and the integration of the light. So this was published recently in Mountain Notices. This involved a large team in 5 countries, international collaboration. And one important aspect of the paper is that we compared this object with several other objects of this scale. So you may recognize most of these objects. These were subject of meteorite recovery campaigns. Some of you might have also participated to some of the searches. And what we're interested in is the optical energy, because this was the most common measurements of these objects. So how do we obtain the optical energy? Let's take, for example, the Preston bolide, which happened over California, a little over 2 years ago. So over here, we have the calibrated light curve from several stations. And this is the visual magnitude of 100 kilometers. And we have the magnitude, as a function of time. So when we integrate the light curve, we obtain an estimate in joules. But the paper did not offer an estimate of the total radiated light. So what we did, we digitized the light curve by a digitization method, and we integrated. We obtained energy in joules, and this can be converted straightforward to tons TNT, because this is easier to keep track of the power. And the next step was to obtain the radiated light for the other objects that did not have an estimate of the radiated light. So the object had the energy in ergs, which can be converted straightforward. Then others had the energy in tons TNT, and for example, Novato had it in joules, which can be converted to tons. But most of the objects did not present an estimate of the radiated light. So we obtained the light curve from digitization. You can see the different ablation profiles. Some of them have the peak in the front, some of them have multiple peaks, and but most of them display a peak towards the end, where the atmosphere is more dense, when they reach close to the maximum dynamic. And here are all the objects again. To these, we added 3 high-energy meteor showers, because these are biased towards low entry velocity, because these were the subject of meteor recovery campaigns. These were studied with high-quality multi-instruments. These include all-sky cameras, radiometers, and infrasound and seismic. So next, we computed the source energy. This is based on the given pre-entry velocity and the estimate of mass, including the error. And we have the source energy here. And when we plot right now the source energy versus the optical energy, we obtain a bit which is a little bit different than the one obtained by Brown in 2002. And also the error, it's a bit lower than the one obtained by Brown. And the Brown had the estimate based on high energy asteroids. So now when we put it all together, we have all the estimates for the Pyrenian fireball. We have the seismic estimate, the infrasound estimate here. It has no error bar because it was only observed by one station, and it's not concluded. The error is not concluded. We also have the estimate of the seismic method, and the lower margin also fits the one obtained by the nominal value of the dynamic method. Also, the dynamic method has a larger margin because this includes several assumptions. As you can see here, the bolide radiation has the lowest uncertainty between the methods. And this was used by comparison with other objects at this scale. So to conclude, we have obtained the radiated light for the well-studied atmospheric impacts. We found a relation to calibrate the TNT scale impacts, and so far the bolide radiation is the most reliable method of estimating the source energy of objects at this scale. And the future work is to integrate also radar measurements and to understand how this changes the flux density. Thank you.